Hello, my name is Clas-Otto Wene. The title of my contribution is Operationally Closed Systems Develop Eigenbehavior. This proposition comes from two of the founders of modern cybernetics, Heinz von Förster and Francisco Varela. I find the proposition both enigmatic and fertile. It is enigmatic because it promises to resolve the paradox of self-reference and circular causality. It is fertile because it generates profound ideas and results that can be empirically tested. It brings into the cybernetic realm concepts and methods from two successful branches of modern physics, namely non-equilibrium thermodynamics and quantum theory. Thermodynamics provides means to study the relations between the system and its environment, and quantum theory provides operator formalism to study the development of eigenbehavior. My contribution explores the application of the proposition in two cases, namely learning curves with implications for energy policy and the nation-state in the Westphalian system. The case with a learning curve represents many years of efforts which have provided quantitative results validated by measurements. The results apply to energy technology policy where they challenge the validity of a well-established theorem in neoclassical economic theory. Based on the progress for learning curves, I suggest to try the Förster-Varela proposition on the concept of nation state. We start by evolving the story of the learning curve. During my studies, I've come across these data for a 235-year-old learning curve. In 1780s, Alf Chapman was building warships for the Swedish Navy at their base in Karlskrona. 10 ships of the line and 10 frigates were built in pairs as twins. This double logarithmic diagram shows a number of days on slips for each twin as a function of number of twins produced. Chapman was an accomplished shipwright, pioneering new modern methods of shipbuilding. But these methods were deeply resented by the conservative Navy. At Karlskrona, Chapman had to fight not only weather and light conditions, but also the opposition of the conservatives. The diagram demonstrates his initial troubles and eventual success. The three first pairs show no improvement in building time. Chapman was preoccupied with managing the environment. However, the fourth pair was built in record time, and during the following 6 pairs he asserted his methods. At the end, he had consistently reduced the time on the slips by 50% relative to the original value. Let us now apply the learning curve, which is about the value of experience from action. In this case, it proposes a linear relation between the logarithms of labor measured by the days on the slips and the logarithm of cumulative number of twins. The linear relation has slope minus e and intercept c. The cybernetic theory provides the eigenvalues for E. From these, the learning rate is calculated, showing the reduction in labor for each doubling of twin ships. The theory has only one free parameter, namely C, that normalizes the theory to the project or technologies that are studied. For an operationally closed learning system in the basic learning mode, the learning rate is 20%. Now, how does this apply to the shipbuilding activities 235 years ago? We normalize the theory, meaning fit the constant C to data, apply the 20% rule, and obtain the results. We obtain a very good fit to the last 6 pairs when F. Chapman has managed his complex environment. But we need to explain all data. The learning curve from the very beginning of industrialization demonstrates a double closure of the learning system. Consider the learning system as a non-trivial machine consisting of 2 operations, producing and computing. Producing is a trivial machine, input is labor efforts and output is shifts. Computing folds together impulses from 2 feedback loops, one internal, closing over producing, and one external, closing over environment, here marked as M. Computing sets a state of the learning system, Z, and through this, the input-output ratio of producing. We can now understand the data. During production of the 4 first pairs, computing receives large signals from the environment through the external feedback. Computing has not yet learned how to manage these signals, and an external observer concludes from the scatter of measured points that no learning is going on. However, the internal feedback is active, and the system does learn from ship production. Eventually, in producing the last 6 pairs, the learning system and its environment have equilibrated, and the internal feedback asserts itself. The external observer may conclude that the system is at last learning, although the internal observer knows that learning was going on all the time. In the thermodynamic perspective, the learning system has reached a steady non-equilibrium state with continuous entropy production. This situation is investigated in the works of Lars Onsager and Ilya Prigozhin. I conclude that the learning curve is indeed the eigenbehaviour of the learning system in the steady non-equilibrium state. The general expression for the learning curve relates the input-output ratio to the cumulative output. Available empirical data confirm the cybernetic explanation of the learning curve. Here is an example from a contemporary project studied by Junginger et al. From Utrecht University. The project involves the construction of an offshore windmill park at Horns Rev in Denmark. The theoretical learning curve with a learning rate of 20% fits the data. The experienced construction team quickly reaches the steady non-equilibrium state. Now, although 20% is a basic zero-order learning rate, there are higher-order modes representing a spectrum of eigenvalues. Double closure can also produce context dependencies. But all this is discussed in the literature. Here and now, I therefore would like to pass on to the role of the learning curves for energy technology policy. Let us zoom out and look at the decarbonization of the total global economic activities. The historical trend corresponds, not surprisingly, to a 20% learning curve. That is by far too little. We must considerably bend down this curve as emphasized by all scenarios to manage climate change. Here, the learning curve comes out as a game changer. Following Förster Varela proposition, what was originally seen as useful but limited correlations emerges as token of fundamental properties of human systems of interaction competing for scarce resources. The consequences for energy policy from this change in status are considerable, as illustrated by these three perspectives on the learning curve. Ken Arrow's paper from 1962 dominates the perspective in mainstream neoclassical economics. Arrow confines his analysis to labor input, that is, learning by doing, and thereby avoids challenging the so-called second fundamental theorem of welfare economics. Governments can achieve a low-carbon energy system through lump-sum wealth transfers, for instance, by imposing CO2 taxes. But government technology deployment programs with investment support are neither legitimate nor efficient. One proponent for this view on the learning curves is a 2018 Nobel laureate, William Nordhaus. Boston Consulting Group represents a management science perspective. In an influential book from 1968, they presented studies of the learning curve for total cost, for which they proposed the term experience curve. This was a substantial extension of the learning curve and made the curve very useful for industrial strategies. However, the curve remained a statistical phenomenon. Cybernetics consider learning curves for labor as well as for total cost, that is, experience curves. The first point here is that the theory provides both learning rates and learning curve shapes that fit measurements. The second point is that the theory is grounded in validated scientific theory, such as non-equilibrium thermodynamics and quantum theory. The cybernetics theory challenges the second theorem and tells us that government deployment programs with investment support can be both legitimate and efficient. I want to extend this point. Here is the experience curve for photovoltaic modules over 4 decades. The world cumulative shipment has gone from a few hundred kilowatt to several hundreds of gigawatt. Price has come down from 70 to less than $1 per watt, which starts to make PV competitive in global mass markets. In 2004, the demands for PV-grade silicon became larger than supply, and silicon prices surged. The industry started to build its own silicon factories for PV, and prices came down. The deviation from the experience curve after 2004 therefore demonstrates how the double-closed learning system manages environmental challenges and asserts itself just as by the shipbuilders of the 18th century. The drastic reduction in PV prices are the results of government deployment programs exploiting the experience curve. There were small programs during the oil crisis in the 70s. Then came the important PV roof program in Japan in the 90s, followed by similar efforts in the US, Germany, and on a large scale in China. My argument is that without these government deployment programs, we would not have PV modules available and competitive in mass markets today. The confidence in learning curves provides renewed significance to an energy modeling experiment published in 1997. We looked at the global electric system 1995 to 2045 with the help of an optimizing energy model with experience curves specified for each emerging energy technology. We obtained multiple minimum total cost solutions. We see two of these solutions here with almost the same cost but completely different mix of technologies. The focus in 1997 was on technologies, but my conclusion here and now is about paradigms. The existence of multiple optimal solutions to one and the same problem shows that experience curves create non-convex solution space. This may at first seem a purely technical comment, but it has serious consequences. A requisite for the validity of the second theorem is convex solution space. I make three observations. First, experience curves and the second theorem are not compatible. Second, confining government policy measures to lump sum wealth transfers is not theoretically grounded. Third, government deployment programs with market interventions are legitimate and efficient. The analysis of the learning curve illustrates the power of Förster's and Varela's proposition about eigenbehaviour as the outcome of operational closure. It seems to me that the proposition should be tested in other areas. To end my contribution by proposing the nation state as a case in point. Formally, nation states do seem to fulfill the criteria for operational closure as given by Maturana and Varela. The nation state sets up borders and they recreate themselves. But beyond that, a first candidate for eigenbehavior for a modern nation state would be providing welfare. The immediate objection would be for whom? Is welfare inclusive or exclusive? In the spirit of Jürgen Habermas, the second candidate could then be communicative action as a required eigenbehavior for a viable, sustainable, modern nation state. That is triple rather than double closure over economic efficiency, integrating norms and group values which substantiate the Habermas claims for facticity, legitimacy, and authenticity. This brings up the existential question, the Westphalian dilemma. Can all these autonomous nation states transcend their own borders and form an eigenbehavior to manage their mutual relations? For the relations among the nation states must be managed. This brings up the power triangle. There's always the historical, hierarchical solution with a peacemaker. That is, empires who rule by the proverbial empires shoot at people, but they stop people from shooting at each other. Or is a recursive solution indeed possible, with emerging eigenbehavior leading to a balance between autonomy and cohesion? It is a long, tedious, and sometimes frustrating solution, as illustrated by the European Union experiment. It requires sweat, but draws no blood. Thank you.